Hello! We're on day 5 of the language development thing. We'll make sure the stream is up and running and then we'll get started. There is one thing I cheated on. I did one thing off stream. And I'll explain it to you real quickly. Once I make sure the stream is working. Start with the treadmill. Yeah, there we go. Yeah, cool. Okay. So I adjusted the, to catch up for anyone who's unaware, we have this code, we're running it and we're generating assembly-like code for it. And last time the spacing wasn't very pretty, and so I just added some formatting in the printf, in the sprintf right here, like giving them different offsets. The dash is to offset it to the left instead of the right. I can show you what happens when you remove that dash. You can see that, of course I have different instructions for every command, but for this add right here, instead of being positioned all the way on the left, it's positioned all the way on the right when you remove that dash. So you can learn more about it with the online references. You can make your own sprintf, but a bit too lazy for that. We got more important things to do. So today we're going to start working on conditionals. We can go back up to where we handle the precedence. Where is the precedence? Oh my god. Do we even have it anymore? Yeah, right here. Okay. So expression, assignment, we have that. We want comparisons. We do want comparisons and equality right now. So I'll show you how to implement that. It's just the same as that binary term, but now you add more token symbols. Instead of just plus and minus, now you have greater than, less than, equals to, not equals to. We need to scan for those two. Let's add scanning for them right here. We need to add a few more things. Do we have P plus? Plus plus? Yeah, I guess we might as well add those two. Let's this will probably give us errors. Let's comment out this code. And I wonder if I can, let's do an if 0 right here. Else and if. We'll just add another block to experiment with, just to give us more flexibility in what kind of code we want to feed in. And we will do, I don't know, like x plus plus. We'll just make that a token. We'll have an x token and then a plus plus token. And let's make tokens for everything. A greater than, less than, greater than, equals to, less than, equals, not equals, equals, equals. Those are everything we want to test for and add. And yeah, I guess let's also add for, while, if, else. I don't know if we'll get to all these, but these are what we're going to work towards. You want to add a for loop, and I can demonstrate why. What even happens? Where do we... Okay, unhandled char. Yeah, okay. Well, anyway, let's... the eventual goal, and it'll take us several hours to reach it, but what I want to do is to have like a Fibonacci thing. We had like a debug break right here. We'll just run this right at the start, and x equals 0, or and y equals 0, and x equals 1. For int I equals 0, I is less than 8, I plus plus. We're going to calculate the Fibonacci numbers. So we're going to have like a temp, set that to x equals x plus y equals temp. And then we want to print out x, or just the final result of the Fibonacci calculation. And if we calculate it 8 times, that should give us 21. 34, okay, off by 1, less than 8. Oh boy. Now we're going to debug Fibonacci. Y equals temp. I can do previous, that's like the previous value is x. I guess the 0th number is 0, 1, 2, 3, 4, 5, 6, 7, 8. That's the Fibonacci sequence. But that's the 0th number. And then if you add them, add 21 and 34, then you get the 9th Fibonacci number, which is 34. 29 and 13, I mean. Sorry. The 9th Fibonacci number is 21 plus 13, which gives you 34. So I'm incrementing just one more. I have x equals 1 plus 0. Well, we can just step through this. Oh, God. Okay. Oh, yeah. I need to call it previous. This is embarrassing. Previous is 1. Good. X is 1. 2. Let me do like I, that's the Fibonacci number that we're calculating X. Y, I guess let's just do this. Let's do fib minus 1. Because I'm off by 1 somewhere. I'm too lazy to figure out why. But there you go, 21. I think I'm doing it right. We could just I mean, I want to make sure it's right. I don't like the fib minus 1 thing. It's kind of sloppy. Oh well. So I want to do something like this. So we can allocate these locals to the stack in the virtual machine. We want to have a while loop which requires conditionals, and then we'll just emit more code that we already have. You know, it's just additions. But the only thing that we need is jumping, like conditional logic. We already have that working in the virtual machine, but we want to break down the code in order to do that. So just as an example, I'm off by 1 of that calculation somewhere, but that's not the focus. What we want to do is to enable us to write higher level code, higher level language code that we can break down to the virtual machine into assembly. And that's what we're going to do. So we need conditionals for that. And so we can do that here in expression. We'll return in this function. We have primaries. I think that's still fine. Unaries, factors, terms, conditionals, comparisons. Okay. So we're going to essentially copy this code right here. And for comparison, we're comparing tokens. So we can do if it equals token, not token plus, but token, I named them all stupid stuff. So greater than, less, equal, equal, greater than, equal, or less than equals, equal, or less. Okay. Okay, and then we'll copy this code and do the same thing. Again, they're just binary statements. For equality, we'll just be testing equals, and not equals. So we'll do token e equal or token n equal for not equal. And then we can discard the rest. Build that. And now we need to actually process those tokens. So we can go to parse, void, parser. And now we'll set up the code to read in these tokens. So we need a case for, when we're checking if it's equals to, we'll need another case in here, and I can show you what we got to do. So we have an equal sign. The only thing it could be after this is if tokens. No, we're tokenizing right here, and so we're reading the characters. And what we do is we do input I++. If input I plus 1 equals another equal sign, then we're going to make the token type equals equals and consume another input. Otherwise, it'll be just regular equal. Let me just make sure this works. Let me make sure we can trigger it. Do we even evaluate a token like that in the code? Just make sure we run this code. Okay, good. Good, and then we copy it all into input. Let me make sure we do that. Yeah. Okay. Okay, so we are running that code. But for some reason, we're not hitting this conditional. That's concerning. Unhandled char. Oh, okay. Because we quit before we get there because we have an error because we never handled those specific symbols. So let's add cases for those. We have less than and greater than, and then we'll just duplicate more of this code that we're working with here. Let's just get it all set up. It's going to be messy. We don't really care about that at the moment. We just want to get it working. So if we have less than and then we have equals, we have less equals. Otherwise, it's less. Going to add that. If we have greater than and then equals, we have gr equal. Otherwise, it'll just be greater, gr. Error in, okay, and then we have the bang symbol. So let's do that. For not equals, bang. I think we have a token for that. Yeah, we did. Okay. And then just do the same thing. Copy all this. I hate the spacing in VS Code. It only just started doing this. Something new that I don't like happens every time, and I'm just too lazy to go ahead and fix it myself. Not equal, or, bang. Okay. Okay, now we're getting to it. And we read that equals equals symbol. T equals type equal equal. Let's make sure that we have the correct char after that. Yeah, okay. So I think this should work now. Let me just let's read in everything. Make sure we're reading in all the correct tokens. Okay. Bar plus less greater than equal, not equal, equal. Okay. But I have two pluses here, so now we need to handle those. Just copy this. And we'll have a plus plus and a minus minus. Oh, we already, oops. Okay. If you see, we already have that over here for plus plus and minus minus. Oh, God. The next one is plus. We're going to have p plus. Otherwise, we're going to have to move these little things around, I go to that line, and then I hold Alt, and then I move the arrow key up or down, and you can use that to drag them around. Oh god, I need to stop doing that. This is just terrible. I need to stop copy and pasting because, oh man, I really hate that spacing. Really irritating. What are you gonna do? Write your own text? Write your own text IDE? That was the initial plan for the software that I'm working on now, but I just don't have the time for it. M minus, otherwise it's just regular minus. Okay. So now we're reading in P+. The code is that we're trying to parse. Plus plus, we have x, token x, plus plus, less than, greater than, less than equals, greater than, equals not, equals, equals, equals. And we have for, while, if, else. And those are all keywords. They shouldn't be vars, those should be token keywords. And we'll add in parsing for those. How do we do that exactly? Token char, true, false. Okay, these are all keywords. We add, we're gonna add if, else, I guess, else if, for, while. Those are the new tokens we're gonna add. There's 5 of them. Let's add them to all those functions. Straighten it out. Get rid of this P. Okay. Add in the other, wherever that other function is, where we need to account for those tokens. We can just neglect the Pratt parser for now. We don't care about that. No, sorry, that's still the Pratt parser. Here we go. Bar, plus, minus, true, false. Let's just add the next to the other keywords right here. Case. Oh god. Typos everywhere. Okay. Make sure that all compiles. Okay, cool. And now we need to token true. I'm just trying to find the place in the code where we emit that instruction. Right here. Okay. Let me go back to token for, pull these all out again, jump back, add cases for them, straighten it out, okay, and then we just match I plus equals the amount of characters we need to advance. I think that should work, but no, now we need to add it in keyword, where we'll have, we need to adjust this. We'll have if, for, let's do for first. So we'll need to do if stir plus 1 equals, or stir at 1 equals O, have this else if stir at 1 equals 4 or false. We'll have A. Yeah, like that. We'll need to test this, of course. Am I doing this right? I want to make sure the spacing. The indentation. I want to make sure the indentation is correct. 97XP-X2X. What you making? I think he's gone now. But we are working on our programming language. We're trying to work on the compiler. We're trying to compile higher level code down to lower level code in our own language. Our own very simple language. We're trying to add conditionals. Yeah, we're trying to add conditionals for now and eventual more keywords for control flow statements. It's gonna take a few hours. Plus 1 false. Whatever, we'll just do extra work. I don't really care. I just want to get it working and we can make it more robust later. 4. I could just do another match right here, actually. Okay. Stir 2 equals OR. And then we'll do token 4. Let me just make sure that compiles. That compiles. Okay. We're just adding logic to check for different keywords. We also want to do if stir at 1 equals F. Else we can just move this in there. Yeah. So if, oh god. We added if and for. We need a while. Just copy this and add a little while check case. Is W. Oh, God, please. Is there a way to disable most Windows shortcuts? I don't use any of them. I fat finger all the time, and it's so aggravating. Okay, so we have while, we have for, we have the loops, for and while. We have if, now we need else. We can do that. Another one, they don't need to be alphabetical. FE, else, oh god, and else if. Yeah, it's not a good day. I am having so many typos. If, what's happening? What the hell, dude? String 1. If it equals okay, well they're both going to be, I guess we could just have 2 brute force matches, why not? If keyword match, if it doesn't match then we'll do another one. Let's see if this works. Three. And then we'll want space if. That will be 1, 2, 3, 4, 5, 6. 6 characters we want to compare against. Token else if. Okay. Let's check for those two. Where the code is, else if. Okay. Okay. For while if else if. Okay. Oh, I see. First, we should let's check this first. If it's else if, oh god, else I really need to disable the spacing thing. There's so much I'm juggling, but I really need to get rid of that. If, else, okay, still not working. String, if, for a while, if, else. Do we know what the pointer is right now? String. C is F. Oh, we never added a break. We never added breaks to any of these. That is another catastrophic bug. Oopsie. Gotta add breaks when you're working with a switch statement. I'm surprised it worked for that long. Okay, still not working. We're getting closer though. What is C? C is E. Is string, else, and else if. Okay, and then the next one, let's step in here. Your string is, oh my god. Let's see. Is else if. Comparing against else if. Oh, we eliminated the white space. Okay, so I forgot about that. I wonder what implications that'll have. Oh well, we can worry about that later. Still not working. Oh, that's because I also need to change the number. This has to work now. Else if. Okay, we have else and then else if. That's correct. And if you look at the code, and I can never find the code, we have x plus plus, less than, greater than, less than or equal, greater than, equal, not equal, equals, equals, for, while, if, else if, semicolon. Okay, so those are all the tokens getting read incorrectly. We updated the parser. I wonder what this could mean, like else if. Let's just see what that shakes out to. If, else, space, if. Interesting. If, else, if. Else if. We want the else space if there. This is interesting. Oh. I think it is my fault. Okay. Okay. I see. Yes, 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 yes. We just needed to add that extra space and account for it, and now we're getting the right tokens. Okay, so our tokenizers right now, we're reading in all these tokens, which sets us up for lexing them. I don't know. I can never remember which part is the lexer, which one is the parser. I think we finished the lexer. Now we can go back to conditional. Expression. Did I misspell comparison? Okay, yeah. It's comparison, not conditional. Quality and comparison. So what we want is, let's just say, to start testing it, int x equals 1, int y equals 0, and then we'll emit a little expression, y is less than x. And we'll see what happens. Okay. We can, I don't want to emit commands for it. We need to build blocks for it at least. Print statement. Yeah. But then we can skip this emit bytecode thing, and so I'll just add another set of if zeros to comment it all out. Another end if, and it'll look really ugly, and the only thing I can think of is to, when I wrap stuff in preprocessor statements like this, I usually like to indent just to, like the same with regular if else statements, so I know what's being commented out and what isn't, and so we just make sure we're reading all those tokens correctly, x and y, semicolon, int var equals number, semicolon, var is less than var, semicolon. Okay. Print statement, we want statement expression, primary, binary, let's see what binary is. And I think we want to, oh yeah, okay. We left a bug in the parser, in the recursive descent parser, and I'll show you where it is. If I can find expressions. It would be nice to start splitting this out into files, but I don't want to do that yet. Print expression, statement, we're getting there. Expression, okay. Assignment, operator, okay. So I guess it'll always be a binary, and you print something out based on the token. Okay. I just confused myself there for a second. We're going to print the token, and we need different tokens. So instead of star, we'll do less, in no particular order. I guess we can find them token greater than or equal. Let's just find where they're defined and then put them in the same order. We have plus plus, minus minus, bang, plus plus, minus minus, equals equals, greater than equals to, all this stuff. Might as well add a colon in there, just for the hell of it. Okay. Add cases for this into the print token function. Case Braille. Yes, thank you. Just going to add more as printf statements to print out the correct token. So this will be exclamation point, this will be plus plus, this will be minus minus, this will be equals equals, this will be not equals, greater than, less than, greater than or equals, greater than equals. Let's mix them up. Don't want to do that. Greater than, less than, greater than or equals, less than equals, and colon, and might as well add a semicolon, why not? I don't think we're printing these for now, but for when we do, let's also make the formatting all nice. Make sure we can print out all the expressions. Okay, so you see x equals 1, y equals 0, y is less than x. Cool. Okay. Now, I guess we could start evaluating. Like, now that we can see conditionals, we're not executing them or anything. We just want to omit instructions for them. But the first step is reading them. We already have binary expression set up for comparison. That's just another precedence. Now I guess we would want to add loops, like loop statements, like for loop statement, while statement, and if else statements. If else if. Yeah, I think we can do that. So let's go to our statements. We're going to add more statements now. We have declaration, expression. Oh, we also need to add blocks. Block statements. A block statement is like this, where you have curly braces, x equals 1. You can do like int x equals 0 on the outside, but then on the inside, you can shadow that. Like this will have its own value and it doesn't overwrite the outer x, like in the inner scope. Scopes are basically block statements. And then you can have them nested too. So you can just keep going as deep as you want, like that, right? That's what I mean with block expressions. This is a block. These curly braces form a block with individual statements inside. And then this forms a block with individual statements inside. So we're going to add block statement, block. We're going to add loop statement. For loops, we're going to add, I guess, elif statement. Yeah, elif statement. Because, you know, if I did if statement, then I called it like if, you would think it's a keyword, so I'll just do elif. Or if L. I don't know, conditional statement? Yeah, con, why not? And now I need to add structs for those. Statement, block, loop, conditional. And now we need to define their structs. This is going to be, we'll just start with loop. And so while and if loops can be represented in the same way, and we can just make the structure flexible, so we can do like statement S. Statement, the declarator, for like this is int I equals 0, for example. We can have a statement for the conditional, and this will be like I is less than something else. And statement for incrementer, where, you know, you do like I++. And these can be null. Like you can do for semicolon semicolon is valid, for example, and that's just an infinite loop. And so we can just check if some of these are null, and then we would have a block statement, and then you would have a statement block that, you know, this occurs inside of that loop. You do like for this, for example, and then like x equals I, print x, you know, stuff like that, for example. I think that should be the loop statement. We can adjust all these as our needs change. Is that a block statement? Well, let's do like a conditional statement. Or we're going to have an expression, which is going to be the conditional expression. And a block inside of it. We need 2 blocks. I guess we'll need to chain them together. Like we'll need for a conditional statement. I'm not sure. We might need to chain blocks together. We can figure that out later. I'm not going to worry about it. We'll just have a block right here. Conditional statement. I'm more concerned with looping. I want to figure out looping first. And then we're going to have the block statement. And both of these things rely on blocks, so we're going to need to figure that out. We're going to need to count the overall condition collection of statements inside of the block. And you could put them into arrays. I was thinking of putting them into arrays. Draw it out. So if we had an array, I want to do this with lines. Like you have the global statements, like you're putting them all in, you're filling this slot, you're filling this slot. This slot has a curly bracket, a curly brace, and so you open up this element in the array with the sub element of blocks. And then you have like, this is slot 0, this is child 0, this is child 1, this is child 2. And then in that same array, you open up a sub block with children like 0, 1, and then it takes up this array. And then you close it, and then you occupy that slot, and then you go back to the global space, and then you have 0, 1, 2, 3 over here. And so it's just not contiguous in memory. You have gaps like this, and so it's really difficult to juggle that if you just want to allocate everything up front, having minimal dynamic memory. So we can just use a linked list. So instead of just putting them all into an array like this, we can just iterate through like link dash next until next is null. And I'll show you how to do that. So to do that, we will need a thing called a block link. You can call it whatever you want. And this will be the start. Have the start. Yeah. Okay. And now we need to define the block link. Don't do that yet. Link. Let's declare it, forward declare it, and then define the struct because it'll refer to itself. So you'll have block link, a pointer to the next one, and then a statement that it contains. And we need to define this under statement. Where do we define statement? What the hell is the problem anyway? Oh my god. It's something bad. What the hell, dude? I got rid of that somewhere. Can I see the changes, please? It won't show me the changes. That is incredible. Okay. Well, whatever. Statement. Statement. Okay, there we go. We need a forward declare statement. We have the block links. And now let's change all this. We'll need environments. So instead of a single hash table, we can like have a max depth of 16 and max and depth of 16 and current. Let's just call it scope instead. Max scope. Okay. And this will start giving us errors. We need to deal with that. We're just making a lot of simultaneous changes that we're juggling at the same time. Sorry to do that to you. What we're currently concerned with is block statement builder. We don't want that. Don't want that. Let's have like global statements. Yeah. These will be all these statements, like, you know, the function calls, the if-else statement, the globals. Let's have a block link, links 2048. This will be the memory that we draw from to construct the linked list. And link count, block link count equals 0. We want global statements, int global statement count equals 0. Yes. And now we need to start fixing up all those problems. For locals hash table, we need to start sending in the scope, which can be 0. And then we want to access it because now we have a two-dimensional array. Let's adjust that. We don't want to send in the value, the environment. That's a runtime thing that we're only concerned about. Don't want to send in that. We can eliminate that from local hash table anyway. I did something. Destroy that. Start accessing the scope. Okay. Hash. Scope is hash. Oh yeah, scope and then hash. Okay. Making a lot of changes as we go. Sorry about that. Let's send the scope through here. We're going to need to start, because you can have nested block statements. Inside one block, you can have another block which has another block. So you want to keep track of the scope that you're in to determine which nested hash table to use, because you can declare there are all these different environments. Like inside of one scope, you have another scope, so you want to have an additional hash table inside of there to allow for shadowing, where you can have like the same named variables having different types. Sorry, different types, different values. Instead of value right there, we can just send it in. Yeah, we don't want to access the value right there. There's a lot I'm juggling. Too few arguments call. Scope is undeclared. You don't want to access the value. Yeah, sorry, I think I'm making too many changes at once, and now we're jumping all over the place. But it's too late for that. Let's just start passing scope around. Primary doesn't need a scope, it's just a value, but when you're looking for a variable name and trying to match it to the scope, you need that. Assignment can have scope, binary can have scope, because it can be accessing different variables. Bytes expression. And now we need to adjust those. Feed it in everywhere. Bytes expression, scope. Feed it in everywhere where it could be missing. And instead of entry value, we're not using that anymore. Let's just get it value of expression. Sure, that's fine. Block statement builder. Okay, this is where I want to do block link count equals 0 and global statement count equals 0. Okay, and so then this is the outer scope, like global. You know, like in the global you'd see these function declarations like int hstircopy or int main. So those are the statements that you would want to append. So we can do global statements. global statement count plus plus equals statement. Block statement children. You would instead do global statements and then global statement count. Okay, so that's all working. Let's just see what happens. Oh, shit. Okay, now it's working again. Okay. Perfect. We got through that sequence of cleanups. This is getting messy. We can worry about that later. So now I guess we're worrying about parsing and constructing those statements. So let's go to, this is where we're constructing the statements. Let's copy this for later because you're going to be doing a similar thing. Let's do else. Else if t.type. When you're parsing a statement, you're dealing with all these tokens. So if a token happens to be left curly, that means that you're opening up a block. Equals block statement. Make a new function for that. Do s equals null. And then we're going to do while tokens next token. Oh, we do next token plus plus because we matched, to open up this statement, we know that, I'll just show you, advances past the left curly that we read to even call this function. And we do next token dot type is not equal token right curly. And then you're going to start reading statements. We're just going to have that same thing as the outer global function. Like in the global space, you can think of that array that you're constructing as its own list of statements. And so you'll need to do the same in here, where we're going to need a new statement. How are we going to do this? Yeah, so you're going to need to allocate it. Equal statements plus statement count plus plus. And you're going to want to do s type equals statement block. S data block start equals block links plus block link count. And we don't need to advance it right now. We can advance it inside the loop. Block links, is that it? Or links. Links. I just called them links. I should call them block links instead. Block links. Links in the linked list, if you will. And so we start it. And then we can increment the count. We can do, we'll do block link. Link equals start. Okay, and then we can do link. The statement that is attached to the link, we can do just read statement. Or is it like statement? Never remember what it is. And we need to forward declare it, of course, statement, statement. Okay, and that will read in that statement to the link. And then if we have an error, we'll need to, I really don't want to deal with this, so we can just do assert processing error equals 0. So that will just crash if we have an error. Refer error handling to later. And I'll just remove this for now so we don't get confused. And then we can do, we'll read ahead. And so just so that we don't add unnecessary links to the chain. do tokens. Well, this will consume, this will advance us to the next token. And so we can just check right here, if next token does not equal a curly, we can then do link next, allocate another link for it, equal block links, then link equals link next. Block statement must return a value, and then we return. Okay. So as long as we're parsing statements inside the scope, we're going to attach them to a linked list and continuously grow the linked list from a static array. And, you know, I don't think we'll have more than 2,048 statements at the moment. That's already a lot to have in any given file. We'll hit the token count limit before that, definitely. We don't have any guards against that. This is very inflexible code we're writing, but it's just to get the idea across. Yeah, now I guess add code for it. And what I want to do is something very simple. Let's just add curly brace like that, curly brace like that, and then another int x equals 2. Then we'll see if we can parse it. Okay, get an error. Why is that? Right curly unhandled token type. Okay. Oh, that is because in my block statement, we want to check if tokens equals curly, then we just want to do next token plus plus. We could be escaping from this, like in our error handling code, we could break out of this for some other reason. So I just want to check if the next token is a right curly, then we'll consume it. And I think we should stop getting error because of that. Yes, okay, so that removes the error. But you see we have int x equals 1, int x equals 1. I don't think that's the code that we had. Int x equals 2. Yeah. Don't know why I'm getting that. Number token 9 is 2. Interesting. Whatever. We want to print it out. Print tokens. We process all the statements, and then we want to print the statements. Let's loop through here. We're doing a statement. It's a declaration statement. Loop through it. And then we have a block statement. We have another statement, which should be a declaration statement. The expression is going to be an assignment expression. Step into that. Left is variable expression, right is a primary. Let's go to the type for primary. It's a token, and the integer is 2. That's interesting. So what happens when we print it? I mean, I have an idea, or I know why it's wrong. I just want to check out why. The global statement count. We have 2 global statements. We have a declaration statement, print it, and then, oh, do we never clear it? Or, oh, we just never overwrite it. Okay, so that second global statement is a block statement, and we're just not reading it. Hi, man, how are you? Tenebris. What's up, Tenebris? I'm good. We're broadening the abstract syntax tree we made a few days ago with conditionals and loops and if-else statements. I'm doing fine, just a little tired. I'm all over the place, but we're working on it. How are you doing? How are you doing? Hope you're doing well, my man. Let's add, for print statement, let's add statement block, and we'll add print block statement. Send in the S for that. And then I think we need to forward declare it like usual, void print statement. Can't build because we're running the application. Print statement. How many print statements do I have? Interesting. I have no block, print block statement. Block statement. Too few argument calls. Now it's building successfully. And we want to, I guess we can worry about passing scope all the way through now. Print statement. Or we can do while link. Yeah, while link is valid, then we can do link equals link next, print the statement attached to that link, link dash s. We'll want to get started, block link, link equals s data block start, which points to the beginning of the linked list. Want to open it with a curly brace. Oh god, if it's like down. Oh Jesus. Oh god. Oh god. Do that. We're just printing out the enclosure. Okay. Hey, look at that. Okay, so we're printing out x equals 1. Then the curly braces for the scope, and then the inner condition, which is x equals 2. So we have that printing correctly. But now I want to handle the depth of the scope and print that out too. And we're going to slop this up a little bit more. Just trying to think of... I guess we should add new lines. Yeah, okay. This is what we're going to do. We're going to add a new line after every single print statement in here, which is this. And now, you see that it's nice and pretty. But now I want to indent this x. And so we're going to start passing around depth, where we will have char, indent, we'll give it like 32 characters. We'll set it, we'll initialize it all to 0. Oh god. And then we'll have for int I equals 0, I is less than depth, I plus plus, or plus plus I. And then for every single instance of depth, we're going to set that to the tab character, \t. So that we'll append this to the start of every sprintf indent. We'll also need to add indent here. Indent. Just copy this around, make it messy. I don't care. Int depth. Oh god. Oh, please. Add the indent string. Print expression. I think we want to add that there too. We're going to need to pass this all over the place. Yes, it's sloppy. Well, no, actually. I think we just, don't even know if we need to go this deep. I think we could just add it to the, now that I'm thinking about this, I think we could simplify it. Print declaration statement. Where's that coming from? Print statement. No, because there's no way to know the depth of the statement we're printing out beforehand. I don't think so. We can simplify it, but I don't know. Whatever. Let's add a depth of 0 to start it off. We'll do int depth. Pass that around, depth. I don't think we need to worry about print expression. Add it to the top right here. And then we're just adding it to the string. So I could just do it before we append that expression to the string. Statement expression. Let's do this. Statement depth, which differs from its forward declaration. Int depth. We prepend print depth with just adding it right here. Log statement depth. Print expression, too many parameters. Okay. I think that's good. And then in here, when we call print statement, we do depth +1 because this is inside of another block. And so you can see that now we're also appending, just for pretty printing, now when we print everything out, we have int x equals 1, that's global. We have these curly braces, and then inside of it we indent int x equals 2 to show that it's deeper in. So just slopping everything up to make pretty printing a bit more visible. And so then, should I add a print statement? Do we want to add print statements? I guess no, because we're not actually evaluating it. This is just to construct the abstract syntax tree to break down into assembly code to feed toward the I don't want to worry about print statements right now. So instead, we're going to work on the environments now. So remember earlier, it was very sudden, but I added like 16. We turned locals hash table into a two-dimensional array because now we're going to pass in the scope. And so let's say get locals hash table. This will depend. So get locals hash table is where we're reading for that variable at the current depth. And so if we can't find it in the current hash table, then we can just print out printf var not found at depth. Right? Then we'll print string and scope. And then we can go one level up and just recursively call entry equals get locals hash table string and then the scope -1. Yeah. Let me just return entry. Okay, so we can keep going all the way back up until if scope is greater than 0. We'll call this. Otherwise, it won't get called at all. I suppose we could do that when we try to set it. No, only when we get. We don't want to set it, like push to hash table. Yes, and when we're declaring a variable, we should probably just use push to hash table instead. And if it's already occupied, then we get an error. Yes. Hash table. Oh, this is push to hash table. push to local hash table scope. Yeah, okay. So this is for declaration statement. We just want to push it. Let's just try to push it. Push to. And then we probably need to pass some more things like the local position, which we can do with local count. And then if it's valid, then we do local count plus plus. Right there. Then we can get rid of all this stuff. Yeah. Local hash table. Compile successfully. So we'll try to, we see that we have a declaration statement. We'll try to push it to the hash table. If it's already occupied, we'll return null. If it isn't occupied, then we will push it to that exact slot in the hash table. We're not going to worry about collision right now. If there is a collision, then I guess we can assert something, but again, we're not going to worry about that. We're going to have so few variables just for testing. Like we're just testing with X, Y, and Z to make very basic functions. Of course, once we want more robust language, we would account for hash table collisions, but we're not going to do that right now. We're going to keep it very simple just for testing and development. So we're going to push it to the table. If it goes into the table, then we'll get back a valid entry. We'll increment the local count. We don't need to do this. And then we'll just generate code for it. And init bytes declaration statement. Okay, emit byte statement. We'll want case statement block here. And then emit bytes block. Pass in scope plus 1. Yes. We have a block statement. Everything inside of this is going to be a scope deeper. Let's see if we get to evaluate this. Of course, we don't have anything for it. We'll need to forward declare this. And then void emit bytes block statement s int scope. Okay. Let's just see if int debug 0. We'll add a little breakpoint there with F9. Whenever you see capital B, I'm pressing Control-Shift-B, but for some reason I didn't go through. Okay, and of course we actually never call this because I have it commented out. But this will look a certain way if it's working correctly. We'll see. Oh dear. Okay, now we need to handle this. So we commented this out, and we want global statement count, statement, global statements, I, emit byte statement with a scope of 0. Okay. Okay. And then when we get to a block, we want to do emit bytes statement, do while. Another while loop, and we'll do the same thing where we do statement or block link equals s data block start while link is valid. We're going to do this where we do link s with the scope that we already incremented when we called emit bytes block. Then we'll do link equals link next. This is how you iterate a linked list. Let's move this down here. It doesn't matter. Okay. So you see that we get this code where you're loading an offset of 8 into register 0, and then you're, oh, it's add now. We actually want to subtract. That was a typo when I was adding in all the pretty printing stuff. You want to subtract the stack pointer, the stack register, by that amount. And so even though you have both of the variables are called x, but you don't represent scope or environments the same way inside of the virtual machine. Ultimately, they're all still local variables, and so you want to allocate space on the stack for both of them. And then once you exit, in the compiler, like, you'll just know if you're outside of a certain block, so you'll stop issuing commands for like the variable in the stack at offset 8, for example. But you see that we do load them both onto the stack, so this is correct virtual machine code that we're generating for the block statements. So what do we do now? We're almost at 2,000 lines of code. Oh my god. So like errors to 0. What do we do? I guess we could add a while loop. Yeah, so now we'll try to start evaluating loops. We'll try to do control flows. I can't remember how we should do if-else statements. I guess just to jog my memory. But I don't want to do that right now. But I don't know, I'm just curious how it should work. Else, and then how would you handle like else if? You would see the if keyword and you would open up a function for if statement where you would get in the conditional, you read in that block, and then immediately after you check for the else if token. And if that's in there, then you would read in the other block, and you can chain together an indefinite number of else ifs. Could that be a linked list on its own? Because all of those would be block statements that you would want to chain together. And then you only have one else statement. Yeah. And I think that would be something else, because you wouldn't want to chain together block statements. Block links. You wouldn't want to chain together block links, because like the block links represent like the statements in here. Statement 1. Block link 1, statement 2, block link 2. You wouldn't want to chain those together. Instead, you would want to have like some kind of new structure for like if link. And that would be a link to the next statement. And then you would have a count of like else if count. And then you would have else if link. Next else if statement. Else if count, and then the else if link structure would be you would have an int count. Well, I don't even really know if you need to keep track of the count. Then would have a start. Else if link start. Well, this is for the expression if statement. Have a count. You would have an expression statement for the if, an expression statement for the else, and then if you happen to detect any else if keywords, you would do that, and then the else if link itself would have a next, and then it would have an expression statement. Yeah. Right? It would have, no, sorry. The else if link would have a next to the else if link, and inside of it, it would have the conditional for the else if, and then the block. I think just mapped out the mental model for how we would eventually handle if-else statements, and we can put it down here, blow up the code a bit more, beautify it a little bit. I don't think this is going to make any sense to anyone but me, but brainstorming for how to handle if-else statements. Eventually, not day 5. What we want to do instead of working all this out, is while statements. And I guess we can brainstorm that too. Brainstorming for while for loops. Day 5. So what would we want to do for that? I think we already have statement loop. It's loop statement. We already have the declaration, the conditional, yes. This is a bit simpler than chaining together if-else statements because you just have a single loop. Kevin Morales, 5913. Hey, bro, what's up, bro? How are you doing, bro? Bro, I'm doing great. We're working on our different statement types. We're going to do looping. We're working on control flow for the programming language now. How are you doing, bro? It's good to see you. I know what we're going to do. Yeah, bro, you know what we're going to do. You already know. You already know what we're going to do, bro. What are we doing anyway? Loop statements. I already wrote them out. Hell yeah, bro. That's F awesome, bro. You know it, bro. We're going to have for and while loops. Again, we can represent them with the same underlying data structure. I just went on a hike. Nice, bro. I'm going on a little hike right now. How many steps are we at so far? We are at 9,111 steps. 11T. We are at 9,011 steps right now, bro. That's a nice little hike you do. I think for me, that's 10,000 steps for me is like 3 or 4 miles. Love you, bro. Yeah, I love you too, bro. Kevin Morales, I love you, bro. Enjoy your... Oh, you just got back from the hike. Well, I'm glad you enjoyed your hike. Is that Java? It's Cyrillic letters. Mac? Yeah, I cannot read Cyrillic. I'm sorry. But yeah, well, no, this is not Java. This is C. This is raw C. You see we have type, def, struct, a bunch of C code down here. Kevin Morales says, let's go, bro. I hit 10K for today. Now I'm just doing nothing. I'm going to get geeked off the Benjamin. Nice, bro. Fuck yeah. Getting geeked off the Penjies here. Mid-bytes expression. What was I doing? Yeah, well, enjoy getting geeked off the Penji, bro. And for the other guy, this is C. We're not doing Java. We are kind of implementing our own Java-like language. Because Java's... The backend for Java is, I mean, I guess you could write it in anything, but the virtual machine is in C, or C++, I think. And we're doing a similar thing, where we're breaking down Java-like code into instructions for our virtual machine. Hell yeah, bro, priorities. Exactly, bro. So, yeah, I guess the only thing we can do now is to scan for and while statements. I guess for loops are the more, the trickier of the two, so I'll go for for loops. So we will do, I guess we can comment that out for now, and add in for. Yeah, let's see what happens when we try to read that. Error, okay, good. Token for unhandled token type, okay. And we'll need to handle that in the statement. And I guess we could handle it in the token type right here. So we can do S equals loop statement. We could do like a for loop statement versus a while loop statement. I guess that's valid. I guess we can figure out later, but this is going to be for, this is going to be while. So we can do while statement and for statement. And then we'll add both of them. For statement, while statement, can't compile it because we're running. Let's return a value. Okay. Let's just return null for now so that can bite us in the ass later. Compiling again. Okay. So we found the token for or the token while. We want to advance to next token because we just read that one. Do we need depth statement? Or is this where we're just generating? No, this is just the recursive descent where we're generating the abstract syntax tree for the different functions. This is just the AST generation. AST generation. Recursive descent. Just to remind myself the step that we're working on right now. We are reading the tokens. We're not yet emitting bytecode, we're just constructing the abstract syntax tree and reading those tokens. So anytime we have the for or while statements, we're just going to say that it's one expression. So we're going to do if next token, if tokens next token dot type equals left parentheses token left parentheses. How do I read those? Do we even handle this anywhere else? Got grouping. Okay, well we do that for grouping. So we want a grouping expression. I wonder. Okay, can you do something like int x equals 0, int y? Can you like group two expressions together? No. Okay. So anytime, can you do that? No. Okay. What was I even thinking? Okay, well anyway, what can grouping contain? Expression, grouping, or grouping expression, it just contains a single expression. Okay, sorry, I'm just a little confused. You will expect, we can do for statement. Oh, but when you do for, you do int I equals 0, I is less than something, do like 3 for example, I plus plus, that's valid, I just did something and opened up this window. So we can't rely on that for individual groupings. We need to read the parentheses manually and then read in the 3 different statements on their own. And we'll do that. So, yeah, whatever, back to what we were doing. Just go like this. Otherwise, we'll get an error. Processing error, plus plus, return null, I don't know, printf expected, opening parentheses, after for, yeah. Okay, and we can do the same for the while statement. We might actually combine these two, but not until we have a clear picture of what's going on. And again, I don't really want to worry about, let's just add an assertion. It'll just crash immediately. We're going to assume that we have valid code. And then we can do while tokens next token. Our parentheses. And then, I don't know, if, because we might exit out of this in case we have an invalid code path. Do next token plus plus. I don't know. Okay. No, actually, we don't want. We can handle 3 statements here. Remember. The loop statement contains, I'll split this off to the right, split and move Control K plus Control K, let's try like Control K right. Okay, that doesn't work, that's awesome. Control K slash right. Still doesn't work. Whatever. Just do it manually. Just do it right. Okay. For statement. So we're going to want to read three things here. We're going to want let's do statement S equals statements plus statement count plus plus, and then we'll do S dot data dot loop dot declaration equals statement. We will do condition is statement and increment statement. And we can just assume that all of this is correct too. Like we'll have an incrementer statement. We'll need to handle that. If we see I, and then the next token is plus plus, what would that mean? I don't really have a way of representing the plus plus tokens. I guess we could do I plus equals. No, we don't have plus equals either. We could just keep it simple and at the moment assume that in a for loop in our language we're touching every single one. This is tricky. Oh well. And then we can do block statement. And then we can do if the token after that is not, just assert 0. Expected closing parentheses after for loop statements. Okay. The declaration will end with a semicolon. All these will end with semicolons. We'll need to add special logic because you could have something like colon. I guess the only way to really figure this out is to step through it on our own. So we'll just handle the basic case first and have, let's just see what happens when, okay, cool, because right parentheses, unhandled token type, okay. Because we read, I think that happens in primary, where we see next token is, okay, unhandled token type. Yes. Yes. Figure it out the more we wrestle with it. Let's add int I equals 0. I is less than 3. I plus plus. Let's figure out how we're going to parse these statements first. Token int. Unhandled token type. Okay. Declaration. So we have a for statement. We're going to go in here. Oh, we need to advance to the next token. Next token plus plus. Let's do that first. Compile it. Okay, good. We have, let's go to the for statement. For the conditional, we have a statement expression. Let's go to see what that is. It's a binary expression where we should have I on one side. On the left is a variable, on the right is a primary. And the data in that primary is going to be 3. Yeah, integer is 3. Okay, cool. And then the declaration is, let's go to that. Type is an integer. Assignment, left is a variable, right is a primary, and the value of that primary is going to be 0. Okay, so that's working. Now we just need to figure out how the hell we handle the incrementer. Token plus plus unhandled token type. Yeah, let's just step into it. Incrementer. That is going to be a statement, a regular expression statement, assignment, quality comparison, terms, factors, unary. Unary can have primary. And then I guess we can check if it's minus or bang, that'll invert it. Yes. And then I think we can have a postfix. Yeah, I guess for operator we can have like a, we should do token postfix for now. Operator will just be like the prefix, and postfix will be like if we have plus plus after it. And I guess for that case we can do like a, we'll just assert that, let's just not handle that. Because usually I just do, I keep forgetting this. I had a habit of like doing like for I++, but I just need to start. It doesn't really matter. It'll get optimized by the compiler. It doesn't really matter what order you put it in. I can't really remember. We'll check for the token that comes after, and then we'll just assert. F cannot yet handle postfix operators. Assert 0. Just crash us immediately. And then we'll do token minus minus, or token plus. And then we'll just add more operators here. Bang, and then m minus p plus, where we'll add that token to the operator, and then we'll put in the primary. Okay. Okay. Oh yeah, and I need to change that code. Minus less than 3. Then we'll just do plus plus I instead. Okay. And then we don't handle the right parentheses. Yes, we need to add that right here. And then we'll evaluate the block statement. Parentheses unhandled token type, because we need to do x token plus plus right after we evaluate that. Okay. Token expected semicolon after expression. Okay. That's tricky. When we have a statement like that, we can just evaluate it as an expression. Yeah. Yeah, we'll just call expression on it. It's a cheap hack, but we can do expression instead. Semicolon unhandled token type. Okay, and then we can just check. Yeah, if tokens, next token, type, equals token semicolon. Just do next token plus plus. Otherwise, it doesn't really matter. Okay, cool. Okay, and then we'll get to print statement and S type. S was null pointer because we call it the main. Global statement count is 2. What is I? I is 1. We never append it to the global statements. Okay. In, oh dear God. Okay. Let's use for statement right here. We just return null. That's why I missed the S still. So we'll do that. We'll do the same for the while statement. Walrus, 26. Hi. Yo, what's up, Walrus? How are you doing? We're working on looping statements for our programming language. What do we want to do inside of this? Yeah, I guess we'll do inside. We also do this. For, and I guess we can put something in between. The x is x plus I, right? Yeah. Okay, so that does evaluate to. You want to print it out. Now let's print out what the abstract syntax tree looks like so that we know that it's working correctly. We're getting there. Of course, it's very brittle. We're assuming that we're not doing any error handling right now. We don't want to worry about that. We just want to get the pipeline working. And now we're going to go to print statement. Yeah, print statement. Where we'll have statement 4, statement loop. Yeah. And then I guess we can just read what the different fields are. A while loop will need some kind of expression inside of it. Yeah, let's actually change that to let's do for statement. We don't want the conditional to be a statement. We should just make that another expression. And the declaration is like I is less I equals 0, but this can just be another expression, and then we can handle it right after that. And just do another semicolon check. That should still compile. Yeah, okay, so that still works. 2,000 lines of code. Of course, a lot of it is comments. You seem a billion times more focused than I am when coding, Walrus26 says. Yeah, well, that's just because I have a better idea of what I'm doing, and I've just been doing it longer. Yeah, don't worry. You'll get better at it the more you do it. You just gotta lock in, bro. You just gotta lock the fuck in. And I've also done this before. I mean, I haven't done this exact thing before, but I've written a few languages before. I've like committed myself to figuring out how we're gonna generate bytecode. Like this is bytecode, or this will get assembled into bytecode. We're trying to output assembly code for this higher level language that we're inventing, which is not inventing it, it's just C. Like, you know, we're just trying to, this is the code that we're parsing. We wrote a parser, sorry, a lexer, a tokenizer, and a parser to break this down into an abstract syntax tree that we're then emitting assembly code for. And I want to get that finished today. And so we're locked in, we're cutting a lot of corners, we're not doing any error handling. We're just trying to figure out exactly what we need for this to work. And now we're trying to print it all out. So we're going to go into print statement. I think my treadmill turned off. I didn't even register with me. Okay. It shuts off after I don't know, a certain amount of steps reached. Print statement. Okay. We're gonna do print loop statement. We can figure out exactly what to do in there. Print loop statement. Okay, cool. So, what do we want to do for this? We're going to, I guess we can check if the expression is null, if data loop conditional. If there's no conditional statement, then we definitely know we're dealing with a for loop. Else it has to be a while loop. Let's say if I mean, I guess that's an edge case. We'll just print out for now. We'll just assume that all the loops are fors. We can handle this other ways, of course, too. But right now, that's what we're going to work with. And so we need to put this thing in here. You know, you can split it out into another function. Oh God, what did I do? You know, instead of copying this whole thing around, you could probably just say void indent stir, and then you can do the string, and then the int depth, and then you would just do this loop. String at I. You just assert, and then like int stir len. Yeah, why not? Just check if stir len is less than depth, and just return. Otherwise, you can do, yeah, and then you can just call indent string. Indent 32 depth. And of course that doesn't really, you don't need to do that. That's just something you could do if you want to shorten the code a little bit, and then you can probably compress it even further and just do, I don't know, you just have some kind of global indentation thing. There's a lot of ways to skin a cat. Whatever. We're just going to keep going. So we're going to do for, and then we're going to have a little parentheses like that, and then we're going to, what are we going to do? Grouping. We could print expression. Yeah, we're just going to assume all the expressions are valid, so we will just do print expression, the print statement for the sData loop declaration. We're going to do print expression sData loop condition depth, and then the increment. Oops. Dot. Then we'll add a curly brace. And then we'll do print block statement. We'll do sData loop block depth. Depth plus 1. And we won't increment depth on the outside here. Print block statement. Depth plus 1. Yeah. Okay. And print block statement already increments it by itself. So we don't even need the parentheses. And that will print block. You are walking, maybe I should do the same. Yes, I'm walking. I have a little treadmill. You get one for like 80 bucks off Amazon. It's well worth it. I have a little standing desk. It's like, you know, it's cheap. You can get this whole setup for like 200 bucks off Amazon. It's very nice. It's a huge quality of life upgrade. If you can afford it, I would definitely recommend it. Um, are we doing this right? Print expression, too many actual parameters. Okay. Yeah, we don't care about that. Okay. Let's see what happens. Can we print it out? No. You failed. I don't think we ever hit this. We never hit this. We never hit print loop statement. We never print out the statements. We do print statement. And then we have the different types. We set the loop. Let's just step through it. Okay, and then the second statement type is a statement none because we never set the type. Okay. Let's go to for statement or loop statement or whatever, and then we'll do the rest. Type equals statement loop. Okay. And then we'll do the same for while. I guess we could differentiate it, like just have the type. Yeah, why not? We'll have statement for loop and a statement while loop. It doesn't really matter, we can change it later. While loop, for loop, and then print statement. Declaration statement block, print for loop statement. Okay. Error. While loop. Statement while loop. S is undefined. There we go. Wow, look at that, people. We're printing out these statements correctly. We have x equals 1, then we have 4 into I is 0, I is less than 3, plus I, to do x equals x plus 1. Seems like a good investment. Yes, it is a good. I can't afford it, but I'll get a treadmill anyway. Seems like a good investment. Yes, definitely. Very good investment for your health. You know, you don't want to sit all day hunched over a laptop programming. You'd rather be moving. We humans evolved to walk and run all day. You know, that's why we have 2 legs. Got to use them. Keeps you healthy. But anyway, look at that. We, with all that indentation and those expressions and stuff, we're printing out the abstract syntax tree correctly. So we at least have it all represented correctly in the code. The next thing that we want to do, and I guess I could add a little semicolons in between it, print for loop statement. Yeah, why not? After every expression, we can do print expression, and then I'll add a little semicolon just to make it easier to read. Print statement. For, we have the declaration, we have the expression. Okay. Just make it a bit prettier, understand what's going on. Yeah, let's see it now. Add a space after it too. Okay. Looks nice, don't it? So now we have everything we need to figure out how to put together the virtual machine instructions. Because now, what are we even doing in here when we emit the actual instructions? Oh yeah, we have no way to handle for loops. So, you know, we're just pushing that x onto the stack where we set x equal to 1. Instead of x to 0. X equals 1. We set it to 0. Then we can do x plus 1. We can just increment it. So this will run once. I is 0. X will be 1. I is 1. 2. 1, 2, 3. It'll run 3 times, so x will be 3 at the end of this. So that's what we're going to do for our assembly. And I'll get right back to it. I'm going to take a piss. Give me like 2 minutes. Be right back, and then we'll start working on the virtual machine. Assembly code generation. Blah, 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 blah. Okay. Okay. Still got a lot to do. What are we doing? We generated the abstract syntax tree for the loop. Yeah. Yeah. I'm totally blasted. We've been going for nearly 2 hours. Okay. Man, even taking like a 1 minute break is it's too hard to get back into it. So, I guess we should go to the virtual machine and figure out how we're gonna make a little for loop. Let's figure out the kind of instructions we need. Yeah, I can't remember what we need to generate, so let's go to the register-based virtual machine. And I made one for it. Register-based virtual machine, there we go. Okay, let's come back here, let's full screen this, and then we'll go to the virtual machine. Okay, let's make sure we can compile it. Okay, so let's just copy this out again and make yet another function. And we'll call this test for loop. And we'll do Dutch compiler, and then we'll just add this right beneath it, test for loop. Okay, and then for the for loop, let's just do, yeah, we want register 0 to be 3. So we can just say, we'll have x is one local variable. Of course, these are globals, so you would want to put them on the stack eventually. I think you would want to declare in the local scope. Secret laying test, don't want that. Let's go back to for statement. Oh yeah, okay, so you would evaluate the scope, the depth of that when you're actually generating the instructions. Yeah, forget about that. So anyway, you just have locals are x and I. So you would load 8 onto the register 0. You would subtract it from 31. You would set the new frame pointer. You would load 0 onto the x variable, and then you would load 0 into the I variable. And then we start generating instructions for what to do next, and then, yeah. Get rid of all that. So this is just a setup. This is the preamble that we're going to generate anyway. And then we need to figure out how to implement the for loop in our assembly-like instructions, and this is like jump is equal to, What is this doing? This is Fibonacci. Okay, this is essentially what we're going to want to generate on our own. And we have increment instructions. That's very nice. We have okay. And then what is the jump if equal? 0 is equal to 2. Do we have other instructions? Like, not just jump, but, what are our jump opcodes? Op jump. What are our different jump commands? Jump forward, jump back, jump to a constant, jump to a label, jump if equal to a constant, jump if equal register to register constant. Wow. Jump if equal register address. These are all opcodes to make life easier for me. I guess it would be nice if I could, like, the next episode, whatever you call this series, I could just make another virtual machine from scratch where we don't need nearly as many operations, but I guess it doesn't really matter. We just need to figure out how to do the jump if equal thing. How do we represent that with a for loop? This is going to be challenging. We're going to need the instruction that we're going to want to jump to as well. Ah, that's what it is. Jump register to register op jump, or jump if equal reg to reg constant, where you're comparing the registers and then you're jumping to a constant, which is going to be the byte code instruction that you want to jump to. So that's what we're going to be using. But we're going to need to compare two numbers in the register and check if they're equal. Where we're going to, this is the Fibonacci number. We're going to start with 0 and 1. Then I don't know what we're doing with register 3. If 0 is equal to 2, I think that's the iterator. And if 1 is equal to 2, what does that mean? Can't remember why we do that. We're using the stack in this. I'm going to push onto the stack, add 0 to 1. We're going to pop. Okay, and we're replacing 1. We're incrementing 3. Okay, these will, okay, so these just skip in case, I guess if, that's the Fibonacci number that you start with, or the Fibonacci value that you're starting with, and you're comparing those two values. This is just an early exit, so we can just forget about what those are doing. I can't remember anyway. So we're storing the value you start with. We're putting it back so that we can increment it or add it back for the next loop. We're incrementing the number of times we've done the Fibonacci add thing, and then we're checking if 3 is equal to 2. Okay. Okay. So we can check. Yeah, for a for loop, if equal. That's going to be tricky. We're going to need to make it more robust, but just to get started, just to jog our memory, we can do a jump if equal. Walrus, just got back. I ordered a walking pad. Nice, bro, yeah. It's really nice to have. Let me turn mine on. I keep forgetting about that. So yeah, we can just start with the jump if equals command. It's going to be really brittle. We can figure out what to do from there. And we're going to be comparing it against a constant. I guess we can push that. Okay. Okay, let's just figure it out. So we have x. X is at this offset on the stack. This is setting up the loop. And so for the first one, we can do load into register 0. Load X into register 0. The instruction that we want to do is where load I, which is the next offset in memory, into register 1. 32. I'm going to add 0 to 1. Going to add them together, and then you're going to do that conditional check. Well, then you're going to... I don't know, actually, which gets evaluated first in the for loop. If you evaluate the conditional, well, I guess first you would want to check. So at the very start, you would do, yeah, okay, so you increment at the end. So you would increment, you would load I guess you could do, yeah, you would increment wherever I is, and then you would load it back onto the stack. So that's storing the new variable, the new value for I. Okay. You have this at the end, so this is, I wish I could add comments here. Yeah, I guess this can be a comment. Update. Oh no, you would need to. Yeah, okay, so we just see the plus plus, so we can add a specific operator for that. We will assume that the for loop, this is going to be very broken. Every single piece of this pipeline is going to be incredibly brittle, but we'll just say that it can only handle prefix plus plus for now, generate an inc operator. Okay, so we'll increment that. This will be the end of the loop where we increment it. This will be the middle of the loop where we load the values and add them together with, you know, whatever instructions they are. And then we'll need a preamble, which is where you do that conditional check. And I guess you could have a halt instruction right here. And then you would need to backpatch that in, I think, because you would want to generate. Or you would need to know, wow, this is complex. Or maybe I'm just thinking about it the wrong way. One viewer, everyone else left because now we're looking at assembly. Yeah, that's how it goes. But you want a preamble for the condition check, and that would be it. You compare the registers, or in this case, you would do I. So you do it here. You would load I into one of the unused registers. I guess we can worry about the instruction count later. You jump if equal. Let's see how it gets evaluated in the virtual machine. Jump equal register. Register 1. Target. Huh. VM equal flag. Want me to test that. I keep forgetting every little step, but I think we could do the same thing with where we compare them. So register 1. Oh yeah, okay, we just check if they're equal. Doesn't really matter which one you use first. So if 1 is equal to 3, 3 or 4 or 5 or 6 or 7. That'll be another thing that we need to do. Only handles exact comparison. No greater than, less than. Do we have greater than or less than? Do we have like tests for that anywhere? Yeah, okay, so we don't have tests for that. Oh wow. We can do jump if equals constant. But that would just be another edge case. So we could, yeah, I guess we could use another unused register and load a constant into that. And then we can just check if it's equal. And then we can jump to instruction whatever. Just see if this works. It's going to be instruction 28, 32, 36. Every instruction is going to be 4 bytes. 40, 44, 48, 52, 56. We will jump to instruction 56. 56. Oh God. New line and constant. Okay. Can't have that. Halt. Oh yeah. Don't want these after all the comments. Okay. And then it's probably going to, it's going to fail. Because we're going to have 0. Interesting. So at the very end of it, in register 0, you would have you're adding 1. This sucks. Expected next instruction on a new line. They're at line 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You need... Yeah, I just forgot that. Okay. Okay. We're getting somewhere. But we overwrite. Okay, okay, okay. So this only runs once. Yes. We need to jump back. Increment. That's the... We load that back. And I guess we'll need to check twice? Or... We'll need to have an initial check. Yeah, yeah, okay. So this will be a preamble. And then we'll just check again. Yeah. Load 2 into 3. 56. 60. 64. Going to increment it. Load it back. Load 2 into 3. Just throttle that register again. And if they are equal, 64. Okay. Is there like a jump if not equal thing? Okay, jump back. We're going to jump back. Jumping countered. Otherwise, yes. Register, we're going to, okay, we're going to put a value into the register and jump back by that many instructions. Jump count minus equals the value in that register. Okay. Yes. Yes. Okay, so we don't need another load like that and jump thing. We can just do load into register 4. We're not using that. We can load some instruction to jump back. 44, 48, 46, 60. And we can jump back by a certain number. Oh God. Can we test this anywhere? Of course we don't. Of course we don't. Oh no, we do. Okay. Jump back until max jumps reached, which is 16. Okay. Load 8 into 2. Add them. 1, 2. Okay. Okay, okay. Okay, so we need to keep track of how far to jump back. Jump if equal that. Only handles exact comparisons. Jump back. Register 4. 60. 64. 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6, 7. 7 times 4 is 28? No. Yes, yes it is. Okay. At least we did something. 2. Okay, cool. So every time it executes, jump count is 3. I can't even remember how a basic for loop operates. Whatever. This is embarrassing. It's 3. Okay, so our assembly definitely is wrong. This is gonna suck. I guess we can puzzle through it. 64. In register 1 we have I. If I is equal to 3, we're gonna jump. It's not equal. We load X. We add X. And then we're going to want to store it. Of course, it's going to offset everything again. 48, 52, 56, 60, 64, 68. Jump back. 32 instructions. We're going to jump to 68. Hey, okay. I guess that fixed it. I just forgot to store X back out. Let's see if we can make it go to 4. We're going to load in. Yeah. Okay. 6. Here. That's because we're adding them, and instead we want to load a constant in. Jump is equal I. Okay. Man. This really sucks. There's so much to juggle. This is way harder than that initial test earlier where we were just adding global values together. To generate the assembly for even a little loop is just ridiculous. It's hard to wrap my head around, but the more you do it, the easier it'll get. And I need to take into account all the different registers that we're using. We're using register 0 for X. We're using register 1 for I. I guess it doesn't really matter. Two. 1, 2, 3, 4, 5, 6, 7, 8 times 4. Yes. Oh man. It's hard to keep all this in my head. We load 0 into the X local. We load 0 into the I local. We load the I local into register 1. Okay, that's fair. We load the 4 constant for the conditional check in register 2. We check if I is equal to 4. And if it is, then we jump. Otherwise, we'll load X. Let's do... We already use register 0, 1, and 2. Let's use register 3. Do we use register 3 yet? I don't think we do. We'll load a constant onto that, and that's just 1. Then we'll add 3. We need to shift all these again. Back to 36, advance to 72. Of course, we broke it again. How did we break it? That's weird. Okay. Okay, I think it's working now. Let's just check if it works for 5. Or, let's do 6. We'll loop 6 times. Every time we'll add 1 to X. Okay, cool. It's working now. We got a really shitty, really slow loop statement working for conditional branching. No, for a little for loop. And now we need to map this back into the higher level compiler to figure out the instructions to emit. Oh man. This is brutal. I can make it really brittle and then we can stop there, and I think we'll have to do that. Yeah. I can add more operations later. Well, I have like a big to-do list of the operations that will be nice to have. And then, if we take it further, I would just write a new virtual machine. I'll just want to write, like I wrote this a year ago, I should just write a new one to have all the stuff that we would really want, because I was just writing the virtual machine assembly, assuming that we would just be writing assembly to it, but I should write a virtual machine with basic operation codes with assumptions like we're compiling down from a higher level language into it, instead of retroactively needing to fit it all together. And I think I would like that, and that'll take even more time if I even want to work more on this. I'll figure it out. I mean, it's at least a good introduction to language programming, and then I guess I could make like day 6 could be writing a better virtual machine. I guess we could do that. We could start on the virtual machine language. There's a lot of different things we could do, and it'll just take a long time. I don't know how far I want to take it. This also work? We don't even need the whole thing. Yeah. Jump to invalid memory. Okay. Yeah. We just jump out of it. Or we can do yeah, that's fair. Whatever, it doesn't really matter. We don't even need a halt instruction. We can just jump so far that we're out of all the instructions. And then that'll close the program too. Okay. Yeah, instead of just staring at this, let's just go back. I'm wasting time. Let's take this back to the other thing. I guess we could label it here. And then when we're emitting bytes, we can start getting really sloppy. Print for loop statement. Emit bytes, primary expression, emit bytes. Emit bytes block. Okay. Okay, this is gonna suck. Okay, emit bytes for loop. Let's move it below the block statement because we're probably gonna want to use it. Okay. I heard that. What did you hear? I said a lot of shit. About the virtual machine, about I don't know what you heard. You didn't hear shit. Okay. So what do we even have when we get to this point? I guess we don't really know. Okay, so we've started emitting instructions. We load the value of 0 into the local x, and then we push that onto the stack. Okay. We're going to want to emit bytes for a declaration statement. Like this. Then we'll do scope +1. Yeah. S data for loop, or yeah, for, we'll just do loop declaration. Okay, we'll see what happens here. Okay, cool. So we push I to hash table entry. Cool. And then we load it. That matches what we do here. That matches what we do here. That's cool. And then for a comparison. Okay, now we'll need to add code for emitting bytes for a comparison statement. Emit bytes expression. Yeah. Okay. We emit bytes for the expression and the conditional expression and the incrementor. Cond, inc. Okay, that failed. Oh, that's because we're still running. Okay, that compiles. And this is going to crash because we just can't, yeah. Okay, so it's a number. I has no valid hash table entry. Interesting. Emit bytes declaration statement. Okay, so we need to debug that first. Just go to full screen, step into here. The value of expression is going to be 0. Man. The string is going to be I. We're going to push that into scope 2. Scope 2. It should be just scope 1. Bytes for the. It's because. Okay. Yeah. Okay. Sorry, my bad. Let's go back. Let's do that. Yeah. Pushed I to a hash table entry of 1641. Let's go into. Yeah. We're doing something wrong. Okay. We have a binary expression. Assert that the operator type. That's strange. That assertion should fail. We have a binary. And the operator is a less than token. Shouldn't that be failing? They're not the same. 29 does not equal 6. Why is that passing? Are my assertions not triggering? What the hell? It's like printed out. Token string equals token plus. String token less than token plus. That's bizarre. What happens if we just do assert 0? Yeah, okay. Operator.type. It's so weird. Does not. This is exactly the same thing. I really don't understand why that's... What the hell? If it is not true, crash. Yeah. Do I need to wrap it in parentheses? Is the expression not getting evaluated when you do a little comparison like that? Yeah, okay. Wow. I even had a bug in the what? Yeah. Do we need to wrap it in parentheses like that? Yeah. Dude. That's crazy. Oh my god. That's crazy. You need to wrap this in parentheses. Shit. Okay, well, that's why that assertion wasn't triggering. And now we need to fix that. Oh my god. That's brutal. Okay. So... Kevin Morales. Yo, how is this guy still alive now at... This guy's so weird, bro. I took a Benjamin hit in the shower and got Taco Bell. Nice, bro. Let's fucking go. What are you doing now, bro? Now that you took a Penji hit and took a shower and got Taco Bell, what are you doing now? And what the hell am I doing? Listening to Dental Floss by Zappa. Hell yeah, bro. Raising it up and waxing it down, bro. So we're going to need totally different conditional logic based on what's happening. So we can just do switch e data binary operator dot type and just do case token plus break, have a default break, and then we'll have a less than case. And we are just going to be super sloppy right here. Oh my god. I need to fix that spacing in VS Code. Okay, so that's for the plus operator. Get rid of this assertion. Guess we can assert down here that it's not handled. We can just do printf unhandled, or here's another trick. Assert unhandled token type in init bytes binary. That's going to be true, and then you just do 0. So we can comment this out, and then you'll see that we'll go to mid bytes, and then we'll hit this assertion, and then you can see, like, right here, unhandled token type. That's just one thing you could do. I mean, or you could just write a comment there, like, unhandled, but whatever. But now you can just keep going, and, yeah, cool. But we haven't implemented that case yet. Okay, so we're gonna take a Benjamin hit, listening to Dental Floss. Bro, haha, so chop Dental Floss. Love you, bro. I'll talk to you later. Nice, bro. Love you, Kevin. Kevin Morales, 5913. Love you, bro. We're still working with the registers. We gotta do register plus plus space register section. Interesting. Add plus plus to this. Right? Oh. No, sorry. You increment in this. Okay. So that's still valid. I think you still have these. And then you emit instructions for them to load them onto the different registers. And then if it's plus, you add less than, man, I guess we could still just do a bit equal. No, it's a binary expression, so. I think we just need to handle this with a specific case in the for loop. In the for loop specifically. Oh, I keep forgetting about that. It costs us so much time every... Oh god, I hate this. So it's a binary operation. This is tough. We're trying to figure out how to emit the bytes for a register-based virtual machine in our higher level language. This is the compiler that we're writing. And let's just assert that it's a binary expression. Data loop conditional dot type equals expression binary. Let's just wipe all this out. We're going to assert that it's a binary expression, and the conditional data binary operator type equals token less than. Debug break. Okay. Yes. Okay, we don't want to call it two bytes there. Okay. Cool. So those are correct. We're just going to write the most brittle test case to figure out how the hell we're going to handle looping logic. Okay. So we're going to load the different expressions. Let's do expression bin as data loop conditional. We'll do bin for binary. We're going to, using the current register, we're going to load those values. And we're going to see what happens. This should pass. This should not pass because we can't handle primary expressions yet. But you see that for I, init bytes expression. Okay, well, let's step into that. Left and right. Should be I, right? It's I, yes. And then the scope. What is the scope? Scope is 1. We're going to find that entry, and we get it back. The entry, of course we can't read it. Local position is 1. Yes, okay. So That's another thing we're going to need to change. When we do the local position, when we do the declaration statement, emit by its declaration statement. Local count, local plus plus. Why does it revert? To 4. Identifier X. Let's print out the local count too. Okay. Entry is going to have local count of 1. Good. And local position. Okay. No, I see. Okay, it was just a little bug. We gotta do... Just gotta start it with +1. Right? Yes. Yes, 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 yes. Okay, and then we load I onto register 0. Will that throttle anything? No, current register is just what we're using. That won't interfere with anything. We're using that first. Yes. Okay, we are loading I onto register 0. Then it's a primary expression, assume it's a number. We're going to do the same thing. We're assuming it's a number. We're going to load onto the next register whatever it evaluates to. So how do we do that? Assert e data primary dot t dot type is token number. Is that valid? Okay. So we're just asserting that it's a number, and then we're just going to access the integer. Okay, integer, entry local position. We're going to load an immediate value onto it. Primary type dot data dot integer. And then we'll do the same down here. We'll do like -9b. I don't know how many spaces we'll need. Let's just assume 10 spaces. Load, current register, the integer, and then the byte count, byte code count. Yeah. Okay. I guess we should also start let's do the byte code count. Okay, cool, and we just never eliminated that assertion. Making a little bit of progress. We're loading onto registers 1 a value of 3. Okay. And then we're going to jump if they're equal. and that's going to be disgusting. And then we'll need some kind of back patching thing because we won't know how far to jump. We'll want to jump to the end of the loop. And there's no way of knowing, so we'll need some method of back patching, but we'll just figure that out. We'll just say, once we have that, we have a less than, then we will omit. We'll jump. Or eject. Compare these two things. The byte code, we'll do current. We'll do first register position. We'll check, we'll compare the registers. First register, second register. And do another jump. Check. First register pause, second register pause. Bytecode count, and I can do that. Okay, that's compiling successfully. And then we will just add like need to backpatch. Need to backpatch the instruction to jump to here. Okay. Let's see what happens. Okay. Cool, so we are emitting something. We're loading the variables in, then we're loading, this is the start of the loop. The start of the loop is instruction 28. I guess we could do like loop start. Int loop start instruction equals bytecode count times 4. Then we can just make sure, well, let's just read what it is. So the start of the loop is instruction 28. Yeah. That's instruction 20. Okay. That's no good. Oh. Okay, I think it's after this. Yeah. Okay. Oops. So, yes, instruction 28. Okay, we just need to move it after we emit that declaration statement to start with I. Okay. It's going to take a long time. Okay, so that will be the jump instruction. That will be the comparison at the start. And then we'll need to print out all the data for the stuff on the inside. And then we can do block link equals s data loop block dot start while link is valid equals link next emit bytes statement s scope, and this isn't right. S data loop block dot start. See declaration of statement. Loop statement block. It's a pointer. It's not a pointer. That'd be block data block dot start. Okay, that's nasty. And then let's just see what happens after. Okay. Interesting. Bar X not found at depth 1. That's fair. That's fine. Under register 1. Register. Let's get rid of that. So we compile it. The current register should be 2 now, so why? Second register position is 1. Let's just step through these. First register position. Current register is 1. Cool. What is current register now? It's 1. Emit bytes expression. And we don't increment because, yeah, we never do it here. Register plus plus. Okay. So now after that jump expression emission, we're going to load X, which is from the correct position. Load that onto register 2, load 1 onto register 3, add them together, push it back to the stack. Okay, that's nice. And then we're going to want to, at the end of it, we're going to want to increment it. Otherwise, we're just going to keep. And then, yes, okay. Okay, so then we're going to assert that the S data loop increment, which is an expression, we're going to assume it's a unary. Dot data, well, dot expression unary. Type equals expression unary. Okay, and then we're going to assume that data.unary dot type unary operator equals expression token p plus. We're going to assume that the prefix operator is plus plus, and then we'll just move debug break after that. Okay, so we passed all these. Again, we're making it very brittle. We can always add on to it later once we understand more of the stack. We're going to want to increment. Then we're going to want to halt or jump back. Do this to make it look pretty. We'll do that. Okay. Oh. Oh, God. Come on. Jump back. And then whatever the register is, current register. Yeah. That red is current register plus plus, whatever. I'll do reg. We'll do load. We're going to load the offset. We're going to need instruction offset to jump back 0. We're going to want to load into that register the instruction offset to jump back. And then we're going to want to jump back with that register. Okay. And I don't know, let's just make it 100. Who cares? Let's make it 69. Hell yeah. And then we want to increment. We want to increment, and that will be, let's do inc. Increment the register. Oh dear. What register were we even using? We want to use the register for I. And I is going to be first register position. First register position. And then we're going to want to store it. This will be load that register. Yes. I'm going to load that register position back to that local. Oh God. Oh my God. This is horrible. Can we just reuse this emit bytes declaration statement now? So when we increment it, we're going to take whatever that local position was. Okay, yeah, we're just going to need to do a lot more logic. Oh man. We're not giving up, we're just going to keep going. It's going to keep sucking and we're just going to keep going. And we need the position on the stack. We're going to get that position, we're going to do int inc stack pos 0, and then yeah, this is incredibly brittle. We could always reorder it, reorder the operands so that we could always, if you want to look for the keywords, whatever. This is way harder than I thought it would be. We're 3 hours in. Oh my God, dude. Oh my God. Dude. This sucks so bad. Whatever, we'll just take the left whatever thing, emit bytes expression variable. Can I like store it back on? How do you do that? Yeah. This is where you do emit bytes expression assignment. This is where you're assigning it back. We need to get the entry, the storage. Yeah, okay, we'll just do all that. Just copy all this over. Right into that code we were writing. Oh my God, dude. This is horrible. Oh my God. Oh, Jesus. Ooh. This is bad. Okay, eData. Do binary data. Bin data. Binary left. Data, that variable offset. Okay, we're gonna need to. This is so inflexible and it's gonna break immediately. First register pause. Okay. Okay, so we're gonna add 2 to 3 And we're going to load X back onto that slot. First register pause. Entry local pause. Where does that load come from? Pause is 2. First register position is 0. That is I. Left is a variable. Please. Variable string is I. Where's that load, that second load coming from? I don't know where it's coming from. Or X not found at depth 1. I just need to step through this. I made a monster of code. Code monster. Okay, so we're emitting for I. We're going to push I onto register 0. We're going to load a constant of 3 under register 1. If they're not equal, we're going to jump. And then we're going to add, yes, sorry, I forgot about that. We're going to add X, which is on register 2. We're going to add a constant of 1, which is on register 3, to register 2, which is X, and push X back to the stack. And then we're going to increment and then we're going to push it back onto the stack. Blah, blah, blah. Let's just see what happens. Increment 0. Okay. You add a new line statement after that. Wow, this is just a monster. Increment 0. We're adding them, storing it. We don't want that other jump if equal. Where is that other jump coming from? What is happening? No, I'm just looking at the wrong instruction, I think. No, we're printing it twice. Where is that coming from? Find every instance to jump if you... Okay. This one right here. Oh, God. Oh, this is so painful. We're emitting 2 jumps. Okay, that's my fault. Already did that. I think that was just a bug. Get rid of all the breakpoints, or just comment them out. This is the assembly that we're generating. Man, that's That's weird. Like, doesn't that look horrible quality? Yeah. Strange. Okay. We load them. We jump if they're equal to. We add it. Equal to load, add, load it back, increment I, load I back. We have another load and then jump back. We don't want that. I don't think we want that. Okay. This is the start of the loop for, let me just print out loop start. Print F. Or let's just throw it in here. Start a for loop. We load I. We load 3, check if they're equal. Load X. Load 1, add 1, x plus 1, store x, increment I, load I back to the stack, and jump all the way back. Okay. And I need to do one more load where we do, reg. I load onto the reg. I load the instruction count. Instructions to jump back. And instructions to jump back. Okay. It'll be a register and then a number. Okay. Okay, so start a loop, we do all that. We store x, we increment I, store I, we load the instructions to jump back to register. We got them backwards, I think. Register instructions to jump back. And then we're jumping back by 4, but oh yeah. It's getting messy. Okay, so we're just pretending that the instructions to jump back is 69. Okay. We have everything assembled, I think, and now we need to do the back patching. We need to back patch the instruction to jump here, and that's going to be a huge pain in the ass, and I don't know how we're going to do that. We're going to need to figure it out next. Yes, and then I think we can just do, with the current instruction count, we can just keep track of where the loop starts, loop start instruction, and do jump back, take the difference between the current bytecode count, and subtract that. Bytecode count times 4 minus loop start instruction. We don't need that anymore. Okay, so we're going to print step back 36. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 4, if I'm not wrong, is 36. So I think that's right. So we jump back by that much. And so now all we need is to back patch the instruction to jump to here. And I will figure that out after I take another piss. We're getting closer. We're actually making progress somehow. This is one of the I think this is the hardest thing I've done yet for the virtual machine. It sucks. So I step away for 1 second, and I don't need this. I'm back. And of course, as soon as you step away, you start thinking, your mind is still thinking about it. And so I was thinking about how we're going to handle this exactly. And, we're going to jump just past the final instruction, but we won't know that until we omit everything. Oh man. We could. Oh man, this is disgusting. But we could like set a token. Like we could make back P1. We could set that here. As a demonstration. Back P1. And then that will be, we're going to want to scan through this. Okay, so you see that number symbol. Yeah. Take this. Yeah. You're going to see back P1. So after we're done constructing the string, we're going to generate a table of back patches. And so we're going to associate a key with them. Yeah. And then we're going to need it. Oh man, this is disgusting. I mean, this is just the price of working with the string here, so that's what we're going to do. And it's going to be disgusting, and it's going to be super brittle, but it's not going to be any different from anything we've done so far. So we're going to do int back p's, and we're going to, like, I don't know, how many do we want? Let's just do 64. We'll have 64 back p's, and we'll have, like, int back p count equals 0, and then yes, okay. And so then we're going to do int print back patch this. Oh god. We can do byte code count times 4. Please int, and then we'll do back p's. Back p count plus plus equals byte code count times 4. Back patch at slot. Yeah, then we'll do back p count. And of course it doesn't work. Why doesn't it work? Printf, not enough arguments. Byte code count. Oh, I added a period in. Okay. And then I guess I could do assert back p count is less than 64. Why not? Okay. I'm not printing it because okay, yeah. Okay. Back patch 64 at slot 0. Do we want to do that really? No, okay. We want to take the difference again. We want to do loop start instruction. Well, no. Okay, yeah. So what we're going to want to do is, this will be 60, this will be 64. Jump back. Then we're going to want to do that bytecode thing again. Oh my god, please. We're going to do, at semicolon, we're going to list the instruction count, 3D, \n// increment it again, and then that will send us to, this is 64, this will jump ahead to 68. We're going to want to backpatch 68 at back P1. I guess we could do back P, oh, we're going to want to match that. And because we're doing strings, we're just going to have to match the strings, and we can just use some kind of sequence of tokens that, yeah. And then we're going to need to replace that whole thing, won't we? Yeah, we can just nullify it. So we can do like some sequence of strings. Yes. Okay, so we can do at, and yeah. Oh man, I lost it. Okay. We can do at. And that will tell us that can I just shrink it? Will this cause any problems when I backpatch it like this? This is one of the dumbest things I've ever done. At 0. We're going to replace at and 0 with whatever number we want. Okay. Yeah, sure, whatever. Just make sure we're printing the right thing. Okay. So we're going to scan through that entire thing at the end before we print it. Byte string. So we're going to loop through. Can we do like, yeah, while byte string at count at I? Oh yeah, okay. Let's do it. Char count equals 0 at char c. Byte string at char c does not equal 0. We're going to do string backpatching, and I haven't done this before, but we're just going to figure it out. So if byte string at char c equals the at symbol, we're just going to set a breakpoint. Debug break. Then we'll just do char c++. Okay, so we hit it. That means that we found the backpatch. Let's consume the next one. Okay, so we'll just have 2. And we're going to replace these. We're going to need to get rid of that 0 too. So this will pose a problem when we have more than one. This is terrible. I mean, I guess we can just we can just check for exactly when they occur. So we don't even need to put the at 0 in there. We can just put an at, and then we will consume that backpatcher thing, and then we'll just replace these two with whatever we want to jump to. And I already lost it. Oh god. At. So just to account for, like, maybe there's 3 instructions if it's a really big file, we're going to assume that we have 3 of them. And then we will need to turn back keys and back P consumed. Okay. We have 3 of these that we want to replace. We're going to want to tokenize, or we're going to want to convert this into a string. And that's going to be tricky. Let's just do another debug break. Back peas. Back peas. The first one is going to have 68. So we're going to want to replace that string, the sequence of ats, with 68. I already lost it. How are we going to do that? We're going to want to do, just have char per back p. I have like 32. And then we're going to fill it in with, or every time we find a backpatch thing, we're going to want to replace per back p and fill it out again. So we're going to do while. I mean, we could make it a function, but I'd rather do it here. And so we can do back p's int num equals, or like, I don't know, back p val. Back p val equals back p's, back p consumed, plus plus. Okay, let me just make sure. Per back p, we can't reset it. Yeah, we can't invalidate it again. That's gonna suck. I guess you can only do it once. You can just do while int just gonna invalidate the entire string array like that every time, just to be safe. Okay. Back p val is going to be 68. We're going to put that into the string. And the way that we're going to do that is we're going to do this is tricky. Man, I'm just burning time. This sucks. We have the value and we want to put it into the string. I've done this before, but it's eluding me right now. The day has just evaporated for me. That's brutal. This is a really embarrassing string. I'm really out of my depth. This is a really embarrassing stream. I'm super out of my depth here. But nobody's watching. It doesn't matter. No one's caring. No one cares. That's great for me. We just flip it. I can just, yeah, okay. This is what I'm gonna do. And it's gonna suck. But we're just gonna do the dumbest thing possible. So we're gonna do, okay. Copy equals back to that. While copy is greater than 0. We're going to do, we have 68. We're going to do copy modulo 10. Yeah, int, I don't know, integer equals copy modulo 10. Copy divided by 10. And then we're going to do count 0, count plus plus. We're going to do cur back p at count equals integer. And then we'll just see what happens with that. Integer is going to be 8. We want to do plus 0. To turn it into a char, to turn that number into a char. 8. Integer is going to be 6. Okay. 8 and 6, so it's backwards. That's great. And then we're going to want to reverse it. And then we're going to need a temporary string. Oh my god. 10th cur back p. Let's just call it temp c, whatever. This is dumb. While for int I equals 0, I is less than count, I plus plus. We're going to go backwards, so we're going to do temp c at I equals cur back p at I. No, we can just do flip. Okay, let's just do flip. There's a better way to do this, but I just don't care. And we're going to do cur back p. Do I equals count minus 1. I is greater than equal to 0. Minus minus I. Okay, and then flip will contain 8 and 6. No. No. Okay. This is horrible. This is embarrassing. I mean, we're going to do count minus I. Yes. Man, I'm really flailing right here. This is like a leet code thing, and I'm just failing right. I'm failing so hard with the leet code thing. I can figure out a faster way to do this later. This is really embarrassing. Let's make it work. How do we flip? Yeah, there we go. Okay. Count is going to be 1. 1 is greater than or equal to 0. Flip I equals 0. There we go. I just don't care anymore. 68. Okay, cool. And then we're going to replace all of those at symbols with 6 and with 8. So we're going to do byte string char c equals, we'll do while, or another for loop. Int I equals count, I equals 0, I is less than count. There's a better way to do this, of course, but we're just going to make it as verbose as possible. Just going to do char c plus I equals oh my god, please. Flip dot I. Okay. And then we can just do byte string char c plus 1 equals at, you just invalidate it and like set it to white space. And the same for 2, just in case we only set one number. Okay? I no longer care. This is stupid. It's stupid to spend so much time on this. Okay, we fucked it up. Because we fucked it up for some reason. 68. I is less than count. 289. Gonna set that to 6, then we're gonna set this to 8. Oops. Okay. Now it has to work. Okay, there we go. We back patched in. Oh man, that was terrible. We back patched in the value that we want to jump to, the instruction that we want to jump to. 0, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52. This needs to be 56. Yes, okay. Sort. Off by 1. Wow. That is so embarrassing. But I wanted to do strings, and this is what you're stuck with. Back patch slot 60. It's yeah. For that increment thing. Where is that increment thing anyway? Yeah, right here. Gonna do that. Okay. Let's do like minus 20. Just making it nice and pretty. Do 24. Just keep trying until it's all nice and spaced out evenly. Let's do 26. Okay, increment 0. Let's actually, -9s, like 13d, do inc. Just try and get the spacing a bit better. Yeah, look at that. Okay. So we're going to increment whatever's in 0 and store it. This is stupid. I'm wasting too much time on this. We're going to increment it, store it. I need to make sure it's right at least. Well, let's just plug it in and see what happens. Let's comment this out and then do another one. I guess we could do if 0, else, and if. verifying it. We're loading everything on. This is the start of the loop at 28. I'm going to jump back. 40. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. We're one too far. 28, 40. I think we're one too far. I'm so confused. Like bytecode count after this. I don't know, man. Load 36. Oh, yeah. That's very strange. 60, 64, 68, okay. Okay, so let's just turn that to 36. I don't know, I'm done reasoning now, but I just want to get this to work on stream and then not care anymore. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Load I, load 3 into 1, compare them, jump to the last instruction if they're equal. If not, we're going to load X, we're going to load 1, add 1 to X, store X, increment I, store I, and then jump back. Okay. Hey, look at that, because, please God, 3, okay. Holy shit, dude. Okay. We got it. Ladies and gentlemen, we added really broken for loops to our compiler. Wow. That's crazy. Let me see. Let's remove this, start of the loop. That was absolutely horrible. Let's change that to like 4. Let's loop like 5 times actually. Right here. Let's change this 3 to a 5, and then we'll see what happens, and then we'll generate the code, and then we'll paste it in, and then we'll check if 5 is in the register 0, and we can't do that. Okay, so it still works, and you can see that with this generated bytecode, now we loop 5 times. And you can see, yes, 5 is in the register. Okay, so it works. There are so many problems with what we have. There's no way I'm going to add Fibonacci sequence. Can we do Fibonacci? Do I want to do Fibonacci? Oh, what the hell. Let's just see if it's even possible. Like, how much harder can it be? Where is that code? I can't even find the code anymore. Okay, so we would want to do y, x is 1, int, temp equals x. Do like the 8th Fibonacci number, we need to make it 7 for some reason. Let's see what this generates. It's processing error because, oh yeah. Temp, semicolon. And temp equals x. Oh, it's because I forgot a new line and for some reason. Huh. Okay, well I guess I need new lines as well, and we can figure that out later. Temp equals x. Semicolon, expected equal sign after variable. I don't know why that's happening. Block statement. Processing error. Okay. Declaration statement. Get the token. Okay. Variable token. Next token. Next token is 27. It's an equal sign. Comparison. Less than equal. Okay, it's not that. It's not that. It's X. Okay. Let's see what this expression is. Assignment. Ah, okay, I want to call, instead of that, we're going to call it quality. Okay. My bad. Well, no, I don't. Is that the problem? Okay. The value of expression, because we do that in the declaration statement, because the value of expression. Okay. We need to find out what X is. Oh yeah, so we hard-coded it, assuming that it's going to be a primary value, which is what we're doing here. So, which means that if it's an expression, we need to load that value from the stack. Yeah. Yes. Okay. So we're going to need to check the kind of value it is, and we can do that here. That's the only place that we actually need to know the value. So we can do if this expression primary, we'll do it one way. Else if it's a variable. Otherwise, we'll load wherever that expression is. Look at the hash entry for it. It already needs to be defined. If it's a variable, it needs to be defined already. We will read from the stack to get it, plus the offset %pd load. And then we're gonna get the local off times 4. Let's call it entry 2. I don't know. Yeah, entry 2. Local pause. Now we're going to need to find out what that thing is, whatever it is, variable string, plus the scope of that variable. Yeah. Can't get it. And we need a string, entry 2, stir, I don't even care anymore. We're going to do var storage plus this monster, and it'll be right.data, .variable, .var offset. And that's not right. Variable, var offset. Data, variable, bar offset. String, undeclared. Oh, oops, I meant to do char. Man, I'm falling apart. I'm falling apart, people. Load. I really don't care about that. Okay. Okay, that's interesting. We have, what do we have exactly in the Fibonacci sequence? We have y, that's going to be local offset 4, x is going to be 1, I is going to be 12, temp is going to be 16. What the hell? Let's just see what happens. I need to go back to that get local hash, get locals hash table and find where I did that. And then I need to close this out. And then we're going to do that. Okay. Let's just see what the hell happens, and it's probably not going to work, and I think I'm out of energy to try and go further, but we tried. Let's do yet another one. I'll just comment this out this time. Oh no, you can't comment it out. Do that. And then we'll just set a breakpoint and see what happens. 7. Okay. Well, it's not quite right. And I don't know why, and do I even want to figure it out? This is us trying to do Fibonacci with the compiler that we made, but it's not going to work. And do I even want to know why? I is 4, x is 8, I is 12, temp is 16. Just do it right there. Load Y on, I'm gonna load X on. Did I type in the wrong code? I really hope I just typed in the wrong code. That's the horrible backpatching. Here's the code. Y, X, I is less than 7, plus plus I. We're going to load X onto temp. I don't think that's generating the correct instruction. You're going to do X equals X plus Y. And you're going to do Y equals temp. So right here, when you generate the instruction for, I don't know, where is this happening? Okay. Load onto register 2. The variable of temp. You're doing right. Oh man, I'm totally lost. Declaration statement. This is in the declaration statement where you have the left and the right. The right is going to be temp. This is backwards. This instead needs to be, what is 2 anyway? What is in register 2? Have we assigned anything to register 2 yet? Register 2. We haven't even used register 2 yet, so we're going to need to load into register 2. We're going to need to load oh man. Flight type is primary. I don't think I can focus anymore. We're going on nearly 4 hours, bro. This is horrible. I just wanted to get Fibonacci. This is the start. This is temp. This is where we're assigning temp. Int temp equals X. We're going to want to load. Okay. And then we're assigning temp. What is even happening anymore, dude? We're loading it into a register. We're loading some value into a register and then, okay, so this also needs to change. This needs to change too. Move that down there. Otherwise, we're loading something else into the register and then assigning that to the variable. Yes. Current register. Yeah, then do we increment current register? Do we not? I don't even know anymore. This is terrible. Okay, whatever. I don't even care about that. This is where we assign that temporary value. I think we need to handle that now, so. Into register, current register. We are loading. The value let's just step into it. Entry string is x. Okay. And what is x? Its local position is 4. Is that even right? Local count is 2. Let's see what happens when we get it. Scope 1. Okay, so we do find it at the scope. Do we? I'm so confused. We want to get it. Scope 1. The hash 144. It's going to be null. It does not equal null. Oh. What the hell? Plus hash 114. Sorry, 114. I'm falling apart. 10. That's the wrong... Okay, so we do have a hash collision. Or x. No? What? Right part. Oh my god, that's embarrassing. Okay, so a little typo there. We're getting the entry for x. We're loading that piece of memory onto the register. And then we're setting whatever local count times 4. Yeah, and then we're setting temp equal to that. Okay. Okay. So this jump is right at the beginning of the loop. We're loading x onto 2, and then we're setting, yes, and then we are setting temp equal to x. Onto that same register, we're loading x plus y equals, 2 plus 3, and then we're setting y equal, okay, we're setting x equal to 2. Onto register 4, we're loading in temp. We're setting y equal to that register. We're incrementing. Okay. Let's see what this does. So, okay. Because, yes, okay. Because now register 21 is going to represent x. Okay. And it just depends on what register you're using. So, like for example, this will be register 2. We can, 34 will be the 8th Fibonacci number. So instead of 7, we can do 8. Or sorry, that's the 9th Fibonacci number. And now we're going to expect 34 to be on 2. And so you see that's right. So now we have Fibonacci in a sense. We can generate the instructions for a very simple Fibonacci with our compiler, with the for loop, with a very basic control flow and backpatching. And this has been a 4-hour stream, and I'm completely exhausted, and it's very brittle, but we have a little bit more flexibility now. And I need to reconsider my life choices, but now we can have very simple for loops in a compiler and do Fibonacci in them. So thank you everyone for watching. This has been absolutely grueling. I don't even know how to end it, but yeah, we got Fibonacci. Thank you so much for tuning in, and I will see you next time.